By Erland Schulson. Erland, take it away.
Oh, thank you, John. And thank you for including me. Brittle compressive failure, as Kai mentioned Monday morning or Tuesday morning, I'm out a day, is a process. Cracks have to initiate, they have to grow, they have to interact. We're talking about that process. I will be speaking about that process on scales that range all the way from the sub-meter to greater than kilometers, over a factor of 1,000,000. And what I hope to convince you of, or at least make the argument, that the process of brittle compressive failure is rather independent of spatial scale. Again, spatial scale, a factor of 1,000,000, and time scale as well, from seconds to days and even weeks, perhaps months, factor of 1,000,000 again. Huge range of scales. So we have to keep that in mind and based upon what I have to say. What I'll be speaking about is first year sea ice, and I'm showing you an example here of its structure. We know it's columnar. Particularly important for most of the ice that forms in the ocean is the crystallographic character of the ice. For the sea axes tend to lie more or less within the horizontal plane of the material and relatively randomly oriented within that plane. There are regions where it's aligned, but most of the ice, I understand, tends to have a random arrangement. In the United States, we call that S2 ice after Bernard Michel, secondary ice, second kind. And the importance of that structure is that when this ice is loaded along the direction x1, perhaps confined a bit along direction x2, that is loaded in the plane of the ice cover, it exhibits two-dimensional inelastic behavior. If this were a piece of aluminum, it would be three-dimensional, but it's not. It's two-dimensional inelastic behavior, and that's an important quality of sea ice, at least as forms natural. Before I begin what I want to say, I want to just step back and prelude my talk with a conversation I had about 25 years ago after meeting something like this. And Peter, you gave a very nice introduction to my prelude. And this goes back as the prelude to Griffith, back in the early 20s, 1920, when Griffith was working out fracture mechanics for the very first time and was considering how a brittle body fails when loaded in compression. And at the time, of course, he was aware of internal stress concentrators. And if one had within the body sort of a slot like that, as Peter showed, Peter's was horizontal, but acting on that slot, of course, is a shear stress working in that direction. And at the tip of this, of course, we have tension here, and if I have it correct, tension here. And what Griffith had in mind was when this stress acting on the system reached a level sufficiently high, then this tensile stress would be relaxed through the development of some kind of axial extension to that inclined crack. That's been since called a wing crack, and that's what I'll be calling as a wing crack as we go forward. And later in time, McClintock and Walsh and others too brought the two sides of the inclined crack together and made it just a plane, such that they were sliding across the plane and friction had to be brought into the story. Friction is key. Not only the resistance to the initiation of the crack, which of course is a tensile type process, frictional sliding across the inclined parent crack is very important to the behavior of that system. We entered the story about 25 years ago, maybe more than that, with the objective of, can we see features of the kind that Griffith had in mind? Ice presented a wonderful, a model material. The kind of ice I showed here of that crystallographic structure, yes, but let's not use sea ice because it's too opaque owing to the porosity. Instead, let's use freshwater ice. Here is freshwater ice. It's clear, you can see through it, and the long axis of the columns is in and out of the plane of view looking here. And I'm throwing you three states of loading of this body, ice, as loaded in compression as the load continues to increase. What we notice is, yes, just as one might have imagined, there is initiated cracks, primary cracks, inclined to the direction of loading. There are several in there. You can see others if you look. And stemming from the tip of these primary cracks are out-of-plane axial extensions. This is not the first time people have seen such axial extensions. Others in the past, between Griffith and now, had manufactured slots of the kind I showed here, and from those manufactured slots in came axial extensions. What you see here in ice is the first time in a material with no manufactured slot, simply material with no initial cracks in it, showing upon loading the initiation of a crack, the growth of a crack as the stress were to increase, interaction of the cracks, and then finally the axial extension we term wings running through the full length of the material, leading to the onset of terminal failure. So you get an idea here of the process at play. So yes, Griffith was entirely right. This kind of process occurs in nature. Here we see it without question. Well, so much for this kind of ice. It's a bit of an idealized situation chosen for its ideality, because these wings, they run straight through, in and out of the plane of view. They don't shield each other. It's simply a mode 1, mode 2 type loading at the tip of the parent crack, the primary. In the case of more other material like icebergs or ice sheets, then one has more granular ice. The structure is not quite as neat to see this kind of feature that one was looking for, but one can find it. And here it is, an example. Here is an example, or two examples, of wing-like cracks in iceberg ice. Here's a piece of ice taken from an iceberg. This is granular ice, and you see the features. So it's not correct to think that these features occur only in bodies that exhibit two-dimensional deformation. The granular ice exhibits three-dimensional deformation, but there they are. They're a distinct feature underlying brittle compressive failure. So I make that point, but so much then for freshwater ice. This is discussion on sea ice. Do we see them there? Yes. Here is a thin section from a piece of first-year ice harvested from the Arctic many years ago, loaded in simply, this was uniaxial loading. And again, I think you can see evidence here of these wing-like features. There are a number of them in there, in that material as well. So even the presence of the brine pockets, the 5% or so volume of air and water within the air brine, hasn't changed that character at all. They are present. Well, going back to those years ago when I first showed things like this, Ron Weaver from the University of Colorado was sitting out there, came up to me and after and said, I see things like that in my satellite images. I said, where? So I went right out to the University of Colorado and went through his archives of images, and I found that one. And that's a Defense Meteorological Satellite image taken of the ice just north of Prudhoe Bay in Alaska. You're seeing Banks Island here. You're seeing an alignment, more or less, a whole series of leads. But I think you would agree that they're not random. There's certain alignment to them. And it was a feature of the kind that I've circled or put the arrows on here that drew Ron's attention to what I had been saying at the meeting like this. And I found here and said, my goodness, they have at least the appearance of what we would call, and have subsequently called, wing cracks. And so if you look at that feature and compare it with what one sees in the laboratory, there's an order of factor of about 1 million here between the features seen in the laboratory. Again, in this image, the columns are coming in and out. And the feature you see in the field. I just say, my goodness, could they be the same? Well, if one goes and applies the mechanics, beginning with Griffith, going through Walsh and McClintock, Nemeth, Nasser and Horry, Ashby and Hallam, and there are some others in there as well. The mechanics of that process that I just sketched on the blackboard have been relatively well worked out. I'm not going to go through them all here, but if one applies those mechanics, then we can calculate, given the ratio of the length of the wing to the half length of the primary parent crack, one can plot a non-dimensional relationship between that ratio, shown here on the ordinate, versus a non-dimensionalized stress. And the non-dimensionalized stress is just non-dimensionalized with respect to the stress applied, uniaxial, half length of the crack, square root of, divided by fracture toughness. I'm not going to use a zero fracture toughness here. And so here's the non-dimensional plot, and the curve here is the equation here, but the data you see on there, they were obtained in the laboratory where one can actually make those measurements. And one says, well, let's look at the field here, and this length here, oh, it seems to be maybe 5 or 6 times the half length of the incline crack. I don't know, you might call it 7. Whatever, we're not seeing the whole of it. It's many times the half length crack. And so if one just runs across and pulls it off and put in some value for the fracture toughness, I think I used the one that John measured in the field all those years ago, came up with a number of about 3 or 4 kilopascals. Not very high. Well, my colleague Bill Hibbler, working on the Arctic ice cover, knowing the wind stresses, etc., I said, Bill, what number do you get? Worked through his equations, took out the weather pattern at the time. He came up with a number about, I think, 5 to 15 kp. We said, good enough, close enough. This looks like there's something, possibly something here, between what one sees on the small scale and what one sees on the large scale. Could it be, this is the first time, that the mechanism is independent of scale? Now, we didn't know in the field. One doesn't know, of course, in a situation like that, whether it's a compressive loading scenario or not. There's no gauge on it. I'll show you in a later case where there is a gauge and it is compressive. So this is the first suggestion that we have a compressive failure process going on. But let's just go further. Of course, in the field, ice is not going to be loaded uniaxially necessarily. There's going to be some biaxial constraint. Wind is blowing, the ice is pushed against the shore. There's a little bit of confinement in the loading plane. So with that in mind, back to the laboratory, we say, well, let's put a little confinement on the ice. What happens, the non-confined case, again, I'm showing a clear example with fresh water, but salt water is the same. Without confinement, wing cracks interact, you get splitting, axial splitting, which indeed is a real mode of brittle failure. But a little bit of confinement, it doesn't take much. We've actually measured how much confinement is needed, and we've modeled it, and it tends to work. You don't need much more than maybe the confining stress is 2-3% of the major stress, and the minimum stress to the major maybe 0.0203. You've changed the mode of failure from axial splitting to what you see here is shear faulting. And notice these faults that are evident. There's a pair of them here. They're conjugate faults, oriented on either side of the direction of principal stress, the higher stress. And notice they're not oriented at 45 degrees, where you'd expect, indeed know, where the shear stress is a maximum. They're steeper than that. So this just isn't a kind of classical shear problem that one has within plastic materials. This is different. And that angle we show later, that angle, that intersection angle, is controlled by the coefficient of friction along these faults. Now we're seeing faults, we're imagining them to slide, and I'll show you evidence of the sliding. So that's a very different kind of failure mode from the uniaxial splitting mode, brought on by confinement and affected by the resistance to sliding. Friction being very important in the story now. So carrying on, we say, well, that's interesting. This is rather reminiscent of pictures Marco and Thompson published 1977 JJR. They had the first Landsat images, and they showed, well, my goodness, we see here evidence of these features. They looked at them and saw them. There was some intersecting, an angle there. You see the angle depicted. They went through and said, what could cause them? Thermal expansion, do we have thermal? No, not thermal cracks. And they included the possibility of compressive failure with the idea of, do we have a strike-slip type faulting here, as in the Earth's crust. And they even said, if we have strike-slip type faulting, friction's a big deal. We can get an idea of what the coefficient of friction might be from the angle of intersection. If you read their paper, they give you a decent number. We said, oh, that's interesting. And then coming a bit later, we saw this a bit earlier from Peter's work. Thank you again, Peter. Ron Kwok did a whole series of measurements using Canadian radar sat imagery, using the RGPS radar sat geophysical processing system, to look at the ice cover over a series of, I guess, 4 winters, was it 3 winters? He keeps carrying this on. And you see in there regions of highly localized shear. Now, Ron plotted them in terms of, I'll go back here. Ron plots them in terms of what here is, this is just the shear that's per day. That's per day. 0.08 per day, divide that by 10 to the 5, you're going to get it per second. Yeah, okay. So that's what he's telling us. And you look at that and say, gee, there are all these concentrated regions. And he makes the comment that there seem to be 2 dominant systems of linear kinematic features. Linear because they're a line, kinematic because they're shearing along the line. There seem to be 2 of these systems at an angle to each other. Again, intersecting, he didn't label, but you can imagine them here, maybe in here, some intersecting angle. Well, again, we're struck by the similarity that we had between that feature and what I showed you a moment ago in the laboratory, but I'll go back to that. Here are other examples of those linear kinematic features, but now showed at higher resolution Landsat 7 imagery. And there's no question now. If you notice, here's a pair of intersecting linear kinematic features. Look at the shearing alone there. It's just dead evident from the rhomboidal openings. Can you see that opening? That's the left lateral shearing, at least as looked down from a bird. If you're a fish, it's going to be the other right lateral. But looking down, that's clearly left lateral shearing, calling that rhomboidal opening, right? And over this one here, it's right lateral shearing, intersecting. So you say, oh, that's interesting. Could that be driven by a compressive stress again, oriented sort of in the middle? And similarly over here, you see other examples of that shearing. So clearly, shearing is an important part of this process. This is a frictional process at play, no question. So we say, here are some more examples. One can look through the literature. Well, here are some more examples of that frictional type sliding. What you see here is Landsat 7 imagery. What you see here is looking out the window of a twin otter as we were flying over the Arctic one winter. And again, you see those similar kinds of features. So you're seeing them on the grandest of scales, the intermediate scale, and in the small laboratory scale as well. So again, you're asking yourself, could this be evidence of a failure process independent of spatial scale? So we go through and say, well, let's look at these things. I'm now calling them Coulombic shear faults, these LKFs of Ron Kwok's, these strike-slip type faults of Marco and Thompson. Erlandschulson also, if you go in the literature, talked about slip lines, but these are not slip lines in the classical metal plasticity sense where they are at 45 degrees, where the shear stress is a matter. These are different from those kinds of slip lines. These are a different feature. So we're calling them Coulombic shear faults. And again, here's evidence of them in, oops, go back. Here's evidence in the laboratory. I guess I've got to go back again, right here. Here's evidence of, this is sea ice, first year sea ice, in the laboratory. And you can see that rhomboidal opening. You see it there? It's there. Here again, they don't always form as conjugate sets. This is the conjugate set. There's just a single one here, as you may have seen in that Landsat 7 image. And here, oh, here they are. Here's a conjugate set as well. So you look at those and ask yourself, again, could these really be manifestation of the same physical mechanism? What is that? What is this fault, this Coulombic fault? So looking at one here, let's just look at its anatomy. And in doing so, what we did is just thin down the ice. And if you thin it down to about 1 millimeter thick, oh, maybe this is 2, I can't remember. Oh, here it is. You see an awful lot of, oh, kind of cloudy white features with defining that fault. There they are, label one B, and there's another one A. Well, if you look more closely, that is, make this section still thinner, and ask, what's in these cloudy white regions? And what one sees in those cloudy white regions are features like this. This is feature A, and this is feature A here. And what's happening, you see there's an inclined primary crack, parent crack, from which stem in a direction of principal stress, the higher of the two stresses, which stem a series of secondary cracks that have developed through non-uniform sliding across the parent. Well, Griffith told us over here, he imagined uniform sliding, where the tension is built up uniformly at either tip. But if the sliding is not uniform, he built a compressive field on one side of the parent, a tensile field on the other side of the parent, and that tensile field is relaxed through the creation of this set of secondary cracks. Sometimes the secondaries are not all on one side. It depends on how the non-uniform the sliding is, but that's the origin of these cracks. So you say, okay, there it is. We're going to refer to them as a comb. They're like teeth in a comb. We call them then a comb crack, perhaps a variation on the theme of the wing crack. Okay, so that's what a fault is made up. That's what it's made up. Do we see them in sea ice? Yeah, here they are. Again, oops. Here's a series of shear faults. There's 3 of them in here. Notice the scale again. This is a factor of 10 to the 6th down over what one sees in the field, in the Arctic ice cover. But again, you see these regions I've got labeled here. Within them there's a primary crack inclined, from which stem on one side only into the tensile field the set of secondaries that relax the stresses that were there. So here we see them, and I'm showing a picture from Erland Schulson, 1988, Journal of Glaciology, where again you could argue. Now I don't know for sure, I'm using my imagination here, you have to accept that. But one could easily imagine perhaps that there was some kind of primary crack stemming from one side, a set of secondaries. Okay, at least there's some evidence of a similar feature in the field as one sees in laboratory. Are they important? We think they're key. We think those features and the mechanics of how these teeth in the comb behave can explain the onset of compressive failure under a low degree of confinement. Now, I won't go through the analysis here, but here's a schematic sketch of that feature. And just in words, what one imagines is that these teeth in the comb, they are sort of micro columns created by the set of secondary cracks. And these micro columns are loaded both axially, there's a P axially, they're loaded also through frictional drag across the free end. The frictional drag is occurring across the primary parent crack. And that axial loading P and the frictional drag loads the tip of these secondary cracks in a mixed mode loading. You got a mode 2 in-plane sliding, a tendency, a mode 1 crack opening, and that mixed mode sliding, when the conditions are correct for propagation, leads to the breakage of the first tooth in the comb. And that's really like a domino process. The first tooth that goes sheds the load to the next, and that's sort of an autocatalytic failure. So we modeled that and said, at least in physical terms, what we're imagining is that the first I don't have a comb, the first tooth to go is going to go near a free end where it's less constrained than anywhere else. And so one could imagine a sequence where the teeth are breaking, creating a process-type zone ahead of what's going to, in the end, develop into a Coulombic-type shear fault. That's what we've imagined here. Haven't actually seen that in process. Have seen some evidence from satellite imagery. I don't have it here, but that's the picture in process in mind here. So if you model it, if you go back and say, okay, the breakage of the first tooth in the comb is what's going to trigger off terminal failure under a small degree of confinement. Then that leads to a relationship you see up here. None of the terms here are non-physical. Every one of them can be independently measured. I don't have to go through all of them. Rather, there's a friction coefficient in here. There's a degree of confinement. That is the minor over the major stress. This angle theta is the orientation of the parent crack. There's a fracture toughness. Where is it? There's the fracture toughness. There's the parent. Nothing is aphysical. It can all be independently measured. What I'm showing here in the graph is a plot of the major stress upon terminal failure versus the degree of confinement defined by the parameter R here on the abscissa, and two sets of results for ice deformed in the laboratory, of course. And you see here a set of results at -10 and a set of results at about -3. using different values for the friction coefficient at those two temperatures, lower temperature a little higher. And these are the data here compared again with the model shown here. We take that to be not the best, not perfect, but it's pretty close. Then we go back to this picture here and say, could it then be that really what we have in the scenario here is an example of brittle compressive failure, where the major stress is vertically oriented, pushing down a small degree of confinement as we see here, and then development of one of these Coulombic faults, of the kind I just described, using this comb crack type mechanism. The other point that's of interest in terms of this scale, from the small to the large, is the failure envelope. On the right, and this is something Jerome Weiss has pointed out some years ago, the similarity in the failure envelope from the laboratory to the field. Here's the laboratory. Again, the same kind of ice I showed earlier, first year sea ice, moderately confined, or the degree of confinement was increasing. And then one sees then an envelope of the kind here. If you're used to thinking of shear stress versus normal stress in terms of failure envelopes, rotate that 45 degrees, whichever direction you want to go. You get a shear stress versus a normal stress. If this were a piece of aluminum, when you rotate it at 45 degrees, those lines would be horizontal. They're not. They're inclined. Again, the degree of inclination is a measure of the coefficient of friction. The point here is that when one compares measurements in the field made by Jackie Richter, Mengi, and others back and published in JJR in 2002, there's a whole scattered bunch of data, but they had a number of sensors in the field, in the so-called Baltimore sensor. Here are the data they measured over time. If we just put them within limits, marked by the red line here, that the slope of this line and of the one in the laboratory is pretty much the same. Brittle compressive failure theory, based upon frictional sliding, dictates that slope. And that slope is governed only by the coefficient of kinetic friction. And I've shown it here. This is that coefficient. And if you deduce from the slope what that coefficient should be, these data give it maybe about 0.6. Then if you go in the laboratory, as we subsequently did, and actually slide along a shear fault and measure the coefficient of friction, it's as close to that number as you deduce from the slope of the envelope. There's no question about friction governing that slope. And the interesting thing is here in the field, we get a value that's rather similar. So then do we have here a mechanical property, friction coefficient, that really is a scale independent property in terms of its value? Of course, the strength is not. If you look at the numbers here, we're talking kilopascal. In the laboratory, we're talking megapascal. What's the reason for the difference? That's a factor of 3, 10 to the 3. But the stress concentrator in the field is 1,000,000 times greater than in the laboratory, and take the square root of that, you get 3 orders of magnitude. And that's why it's down. So we take that to mean that, the mechanisms of brittle compressive failure on the scale small and the scale large are the same. This comb crack idea, there's nothing unique to ice, we think. In fact, here are examples. There's some comb cracks, more comb cracks in ice. Here's some cracks in granite. T.F. Wong showed them. They call them horsetail cracks, or perhaps splay cracks, or feather cracks. But they all look the same, stemming from one side of a parent crack, if you wish. And here's some other example, bigger scale. You see them stemming from one side. They just reported them. I think they're the same thing. I think, again, they're exactly the same. What if that's true? Then that model I showed you earlier should apply to materials beyond ice. For there's nothing in that model that was specific to ice. You just put the appropriate materials parameters in for the other materials, and let's see how well it works. And there it is. Again, the dark line is the model. Plot here, that's the equation there. And here is a set of materials other than rock and mineral. Ice is in there as well. Again, it's not a perfect fit, but the trend is about right, and you're sort of within a factor of 2 or so to what's been measured. So we think there's perhaps, again, not just a connection between the scales, but perhaps from one material to another through the operation of that mechanism. Here's one other point I want to make, field versus laboratory. This is the Shiba experiment. Perhaps you know about the Shiba surface heat energy budget of the Arctic, late 90s. Here's a picture taken, again, I go back to some imagery taken, radar-sat imagery from Ron Kwok on at 3 different times. Day 302, here's 14, 12 days later, here's 3 days later beyond that. And you're looking at you're just looking down at the ice, Landsat 7 imagery again. Call this time 0, nothing in there. A little 12 days pass, and you start to see a little distortion to the grid. I mean, it's from the distortion to the grid one's going to be able to work out the displacement field, and from the displacement field, the rotation tensor, and the strain tensor, and from the strain tensor, the stress. Here it is a little later, and look, there are 2 faults, A and B, that I've noted here, one A and one B, running through the system. And what I bring your attention to in particular is this one here that I've circled. Now this image, this fault that we're seeing, clearly was observed some time after the fault formed, but not too much later than the fault formed. I think possibly A formed before B. B looks a little fresher here. But if you look again at that region here, I want you to look right at this point here, and in here you see what looks like an inclined crack from the tips of which extend out of plane extensions, out of plane wing-like cracks, as Griffith imagined. I would say if that's true, if this is a wing crack, then knowing the length of that relative to the parent crack and its length, then one should be able to apply wing crack mechanics. This is a shortened version of wing crack mechanics, but one should be able to apply those mechanics and get some estimate of what the stress in the ice was, assuming again it was a compressive state of stress. And if you do that, you get a number, oh, here we are. I got a number here of 19 kilopascals. It so happened that at that same point in time, Jackie Richter-Menge was in the field of measuring the state of stress in the ice. It was moderately confined, biaxial. Here are Jackie's data running over the period where that image was taken. She was in the field where the satellite flew over. And here's the date where the blue lines are, right here. And the number she measured was 30 kilopascals at that particular point in space and in time. The other thing that's noticeable about this is if you do the strain field analysis, which I did, work out the strain fields from the displacement fields, backward you can work out where the direction of maximum principal strain is. Maximum principal strain compressive is down, showing there's the arrow where the principal strain existed. Now I'm assuming stress and strain are related here. I'm assuming it's an isotropic body. It's not quite, but it's good enough. So there's the direction then of the stress. And you'll notice that that direction of stress is at an angle to the fault. It's about, I don't know, you can see what it is, a few degrees, 20, 30 degrees something, not 45. It's at an angle that's set by the coefficient of friction of sliding along the parent crack. So we conclude from observations like this that we have here direct evidence of brittle compressive failure of a Coulombic character in the field. Now I got a few more minutes here, so I want to just bring to your attention there are other modes of failure, brittle failure, probably not too important to the failure of the Arctic ice cover as a geophysical feature, but important when that ice cover moves against an engineered structure. For when that engineered structure is contacted, there is within the contact zone a degree of confinement higher than within the ice sheet as a whole. And you can now imagine that if the degree of here we are. If the degree of confinement within the horizontal plane, if the degree of confinement is so high that it shuts down the effective shear stress causing sliding, and these shear faults within the plane of the cover are not going to develop. Yet under those conditions, the deviatoric stress is still zero, I mean not non-zero. As well, what about failure through the thickness, that is out of plane failure? And that now happens. When you can work out the condition to shut down sliding in the plane of loading is governed only by the coefficient of friction. You can calculate what that is, about 0.3 or something like that for a reasonable coefficient. And so if one applies confinement greater than that value, then the failure envelope no longer is it increasing that is strength with confinement, is decreasing strength with confinement. And now failure occurs across the columns. The columnar ice are shown vertical in this image, but the failure mode is now across those columns, and here's examples of that mode of failure. It's a splitting mode, leading to through thickness displacements. It's been called in the literature flaking, maybe some other things as well. But it's a result of shutting down frictional sliding in the horizontal plane, activating a mode of failure through the plane. Okay, but there's one other mode of failure we should know about again, and this again isn't going to happen in the field in an Arctic ice cover, but it could well happen within the contact zone, and I think it does happen within the zone that Bob has referred to as the hard zone within ice, where the ice is very hard. And that is, within that zone, the material is loaded triaxially, not just biaxially through confinement, but also triaxially through additional confinement. And if one does experiments under triaxial confinement, here we are, under triaxial confinement, that is, keep the lid on. Don't just load in plane, but also put a load normal along direction x3 that I defined earlier, so it can't split. Something's going to happen. What happens is you shut down frictional sliding in any plane, but there still is a deviatoric stress that's non-zero. And that deviatoric stress is sufficient through the combination of adiabatic heating to lead to localization of a plastic nature. Now the kind of faulting one gets is not Coulombic. This doesn't depend upon cracks at all. It's the localization of plastic dislocation-driven plastic flow. And what one sees here, there it is, high degree of triaxial confinement, and there is a fault running right through the ice. I'm showing here on the left the no confined case, moderately confined in-plane shear faults, highly confined through thickness type faulting, but of a different character altogether. It looks brittle. We call it brittle-like because the load drops. The load drops suddenly. The ability to sustain load has been disappeared, but it's not brittle in the sense of crack mechanics, in the Griffith sense. It's not that. And the examples, of course, here I'm showing it to you both in freshwater ice and in saltwater ice. The ices don't matter. You see the same mode of failure. And what we see here is evidence of dynamic recrystallization, that the plasticity is so localized, is so high, that the material very rapidly recrystallizes in a solid state manner. Bob and I disagree. He thinks it might be melting. I don't think so. I think it's a solid state process because Bill Durham saw this in ice that he deformed at minus 150 or 180. Didn't quite know what it was, but it's brittle. It's a plastic fault. So that's another mode of failure, brittle-like. You're not going to see it in the field, but you may well see it within that high contact zone, that so-called hard zone that people speak of in the literature. Okay, well, I want to save the last couple of minutes I have to talk about the transition from one kind of behavior, brittle, to another kind, ductile. Now, the criterion I'm going to come up with is not based upon one that you might see if you happen to read the literature on semiconductors and when silicon, for example, decides to become, upon heating, a ductile material as opposed at lower temperature a brittle material. And the criterion there tends to be that if one examines the crack tip, we ask, does the crack propagate, or from the tip, does one send out dislocations? And if the answer is yes, you send out dislocation, good. We have reached the condition for ductile behavior. In the absence of the sending out of dislocations, then that crack will propagate, and we'll call behavior so followed brittle. Now, I'm not getting down to that level. I'm going to call brittle what an engineer sees. Fracture. It's broken. Ductile, a sustaining of load-bearing ability. And that happens to be rather important from a practical point of view. But just to illustrate that the phenomenon certainly is seen in nature, here's an ice cover. Well, I forget where we were standing years ago. And if you look in that cover, it's mostly a rubble field, yeah? Brittle behavior. But within that rubble is a bit of toothpaste. What's that? That's clearly a manifestation of non-brittle behavior. Something ductile is going on. Well, having seen that, known about it in the laboratory, and then here are some results measuring pressure. I mean, you see the importance of what's going to happen. Here is some indentation pressure as a function of indentation rate in Sanderson's book. Gathered all kinds of data, and it's clear that at a low rate, you get some velocity strengthening. That's what you expect for creep deformation, strain rate hardening. But then there comes a regime where there's no longer strain rate hardening. The data are so scattered that you can't tell whether it's decreasing or not. I know Kai thinks there may be a question of whether it decreases. I think it does decrease a little bit from the measurements we and others have made in the laboratory. But there is clear transition in behavior from ductile to brittle at some rate, maybe 10 to the minus 3, 10 to the minus 4, somewhere per second. Say 10 to the minus 4. Not very high. And if you explore that transition and ask, well, what affects it? Now realize that in the field, there are two parameters that are important most. One is the velocity with which ice moves against either itself or something else, from almost nothing to whatever it is. And the other parameter is the degree of confinement. Temperature doesn't change too much. Grain size doesn't change too much. But anyway, in exploring those factors, one finds out that salinity raises the transition velocity. One also finds that confinement raises the transition velocity. These have been measured. Temperature, yeah, a little bit of effect. Raise the temperature, raises the transition velocity. If you refine the grains, make them smaller, then that too, or even the cracks, that too raises the transition velocity. So you ask, what's going on? What's going on, I think, and this is the model we propose, we go back to the comb crack mechanism, a derivative of the wing crack mechanism, and say, look, what's going on, we think, at the tip of these secondary cracks, whether it's a wing or these secondary leading to a comb, there's some localized creep deformation. Ice is a creepy material. So even though it may exhibit brittle behavior, it doesn't mean there is no inelasticity besides crack-driven. There's some creep going on, but not much. And if one takes the argument that when the creep zone size is equal to say the regime of elastic stress, the size of the elastic regime at the crack tip, we say when those two are equal, that defines the transition strain rate. Well, we came up with an argument using a Rice-Riddell model for crack tip, crack tip creep size in tension, admittedly. I remember I had a conversation with Jim Rice. I said, can I apply your model in compression? He says, why not? So this tensile zone at the tip of the crack, this wing-like crack. So we applied the model, and in the end, you come up with a function like this. I don't want to go through all the details, but in it, there's no adjustable parameter. Again, there's friction in here. So where's the friction? There's friction, there's confinement, there's B in the power law creep relationship. That's a simple creep relationship, secondary creep. What else is in there? Stress, it's all physical. And use the parameter N in the power law relationship of 3, typically seen. And so one ends up with a relationship that says, okay, there is the transition strain rate, and in the laboratory, it calculates to be about 10 to the minus 4 per second, which is close to what we measure. And then you might say, oh, in the field, that should be about 10 per day. Okay. And then you go back. Oh, incidentally, here I'm comparing theory with experiment. Again, there's nothing in the model that's unique to ice. And so again, you can apply it to these various natural minerals. And what I plotted here is the dimensionless transition strain rate versus confinement. There is the calculated line. Inside here is the brittle regime. Outside here is the ductile regime for all these materials, including ice. And you see, the boundary seems to be pretty well defined by that relationship. So there's nothing specific in it to ice, if you want. But then you go back and say, well, what about this stuff that Ron Koch I'm showing? He's talking about strain rates here of, if you look at those numbers and say, well, 0.04, that's kind of like 10 to the minus 2 per day. And yet this material, that's a whole lot lower, you might say, than what I've just mentioned to you, 10 to the minus 4 per second. So are we orders of magnitude out in terms of this model, in terms of predictability to the field? Well, no. Now you have to bring into ice the story that Jerome and others have pointed out, the scaling aspects. In Ron Koch's work, when he measures the strain and the strain rate. He's measuring it over a domain of 10 kilometers over a time period of 5 or 6 days. Dividing the strain by that time, you get a number. And that's the number that leads to what I just showed you a moment ago, up to a 0.04, whatever he got. But on the other hand, if you take into account the temporal and the spatial variability of deformation within the ice, as Jerome Work and others have shown, then the story about strain rate is very different, that it depends on time and it depends on size. And just in the limit here, plotting, I'm using his results. Plotting here is a strain rate versus size of the field you're looking at. And observed at different times, the shortest of times, an hour or two, to the longest of times. The slope on that graph is a measure of the heterogeneity. Do I have that right? If the slope is 0, completely homogeneous. If the beta term in this power law is 1, that means one linear kinematic feature, one fault is doing it all for that point in time. It's like a Gini coefficient of 1. One person has all the money. In this case, one fault is carrying all the action. And if you do that, and you extrapolate this back to the point of the laboratory, you get about 10 to the minus 4 per second, corresponding to when the ice on a local scale has gone brittle. So in other words, from these scaling laws, for a length scale of about, I'm showing Ron Kwok's work. Where's Ron? Right in here. Yeah, Ron Kwok. This is where Ron Kwok's data would have been. As you see, much lower than the theoretical prediction if you didn't take into account spatial temporal character. But when you do, you get a result up here. And incidentally, following the scaling laws that were published in 2008, came just this year, just reading the paper coming over on the airplane, Boyakonen and JJR. They looked at spatial scales from, I think it's about 200 or 50 meters on up to about 2 kilometers. And I'm showing over short time scales. And I just put their line on the graph. It would be totally in keeping with what had been seen earlier, extrapolating again to that limit that one would see in the laboratory. So in other words, the brittle behavior on the large scale originates from highly localized, high strain rate deformation on the smaller scale. So with that, I'm going to conclude that the brittle compressive failure of sea ice is a Coulombic frictional process on scales small and large, that the mechanisms underlying brittle compressive failure are independent of spatial scale. I will say the transition from brittle to ductile behavior under compression is governed by the competition between creep and crack growth at the crack tip. And if any of this interests you, where you go down the street in Cambridge and get a copy of this book, I found it on the shelf, it exists. And for that, then I'll say thanks for your attention.
Yeah, well, it's very interesting that the scale, your argument about the scale. I was just wondering about your comments regarding the crystal irritation with respect to the stress. So basically, in nature, obviously, it could be very complex texture, and in the lab, I imagine you can fabricate a certain sort of crystal direction distribution or texture. So is your argument implies that the relative orientation is completely insignificant?
No. My argument implies that the kind of ice that we can grow in the laboratory, columnar-grained sea ice, within which the crystallographic c-axis is confined more or less to the horizontal plane and randomly oriented within that plane, is the same kind of ice that grows predominantly within the Arctic, first-year sea ice, the so-called S2 ice. They have the same structure. Of course, in the Arctic, there's more structure than we get in the laboratory. There are brine drainage channels, etc., etc. And you might argue, do they play a role? They're going to play some role. But do they play a dominant role? I don't think so.
So the image that you show of the crystal, I mean, it was very colorful. So that's
the reason they're colorful, I'm looking at cross-polarized filters.
Yeah, right, but that implies that the C-axis orientation.
Well, it does, but the C-axis orientation, if you use the wolf net plot, the C-axis is confined more or less to, I showed you the graph, the wolf net, and the C-axis were more or less along the perimeter of that plot, as in nature. So that structure that we grow in the laboratory simulates very well, reflects very well what nature produces.
Danny.
Thank you, Erland, for a fantastic talk. My talk tomorrow is going to borrow very heavily upon your ideas.
Thank you, Danny.
But I do actually have a comment and question. You mentioned that the two-dimensional in-plane failure when the confinement ratio exceeds the critical confinement. You mentioned that might not be so relevant for real sea ice. When the confinement exceeds the critical confinement. So I'm going to show simulations from sea ice models where it does a lot.
Danny, I shouldn't have perhaps said what I said, and that is I should perhaps not have said that within a sheet of sea ice floating in the Arctic, the confinement never gets quite large enough to suppress in-plane faulting. What you're saying, it might well get high enough.
The point I want to make is actually if you take a traditional sea ice model that appears in climate models such as the Bill Hibbler model or similar types of model, you typically find stress confinements that regularly exceed the critical confinement ratio. Now, if you take a different type of rheology, which I'm going to talk about tomorrow, we find the confinement hugs that critical confinement ratio, and so much less often exceeds it.
Interesting. I look forward to hearing it.
I comment on this because when you look at the stress state from stress meter, like the data from Jackie, Richtenmenge, and so on, in fact, the highly confined stress state do not exist on sea ice. If you remember the plot of, you have a lot of stress state along the Coulombic envelope, but for highly confined state of stress, they do not, I mean, at least on those data, maybe on some other...
I agree, Jerome, that's my point. Okay. we shouldn't be having such high confinement ratios in our models because they're not really seen. Where they are seen, you have different failure mechanisms, out of plane failure, typically in models.
Yeah, where they are seen is through a contact zone within an engineering problem. Yeah.
Yes.
Yeah, I actually planned my question or comment after Jerome's presentation, but I'll do it now actually because I have very much difficulty in seeing that the physics can be the same in these two scales, because there's a factor of 6 to 7 order of magnitude difference between these two. And I understand that the small scale, it's the crack tip, and actually the stress concentration at the crack tip which is driving the whole thing, sort of where the crack goes and all that. And in sea ice, then ice cover, I don't think that it is really that way. I have a couple of more specific then comments on this, because I mean when you do small scale testing, you conserve the area actually. But when you do, well, you don't do tests in the Arctic, but when you compress that kind of Arctic ice, there's ridging and rafting. It's very different failure mechanism actually than in the small scale samples. So how does this sort of influence the whole argument? The other thing is also that there's no tension in field. Ice cover, if there's tension coming, there's no field ice. It's just leads are opening. There's no tension. That is also a question, because you had, but that is actually a matter of scale of the stress measurement in the field, because you should actually measure the stress in the field in that kind of scale. But if you measure it in a very small scale, as Jackie did, you might get those, but you have to really use that scale also in the measurement. So anyway, I have very much difficulties in really. It is very convincing, your argument, and very, as Danny said, fantastic talk. But
Kai, I will address those points if I may. On the last one, what is this region here? Tension, and you see a lot of data there. Is that not tension in the ice cover? That's measurement. That's not laboratory. That's in the field measurement.
But there is this matter of scale. If you measure 10-meter scale in field, usually you don't get any because ice is opening just leads.
Well, that's all right.
That is very local scale. And if you may go into a flow, there can be tension, of course.
I don't think that matters to the mechanisms I'm describing.
No, let's have different people.
Okay, but I know why he's wrong.
Small comment on the technical side of the stress measurements in the field. First of all, the cylinders which Jackie used were frozen in the ice, so it's a problem to measure tensile stresses with the cylinders, one thing. Secondly, your stress distribution in vertical is not uniform. You have a thermal stresses there. So actually what is presented here is a combination of dynamical loading and thermal stresses.
She took them out. I think the thermal stresses were extracted before the data here are
How do you
presented.
do that? I mean, if you have a sensor in the middle of the field, you have an anisotropic, practically thermal loading. If you're at the edge of the field, it's different. Your loading is not anisotropic. So it's
The
quite
maximum thermal stress is alpha delta T times E.
Oh,
some
depends where
measurement.
you are in the floor.
I can calculate that
No,
out.
it's not right. No, depends where you're on the floor.
I can take it out.
Well,
They've been taken out. Guy, those points are right. Obviously, if you have a large fee, but on a smaller scale, but it doesn't matter to this mechanism. This is a compressive. The stress, the tensile strength
All right, Jerome.
is key.
Go ahead.
Sorry, just to answer to you. In fact, on this plot, the left plot, the tensile stress, you can see it along the diagonal. Because tensile stresses are isotropic. And in fact, if you are looking on those data in more details, you see that those stress states are just following daily fluctuation.
so
Okay?
yeah.
So here you have
Yeah,
a
right.
superposition of two kind of things.
Yeah.
You have those
Baltimore,
thermal stresses,
what
and
they-
then on the side you have Coulomb.
Understand the argument. The Baltimore side was in the middle of the floor. There were the other sides where you have slightly different relationship because your floor is bent.
No, if you plot, I mean, if you plot this for sensors which are at the edge of the floor or in the middle, they are exactly looking the same.
If you look at the CIMI data, which is similar to PEM, but not Shiba, you see this non-anisotropy in the thermal stresses, in the sensors. Whether it's a technical fault of the sensors or not, it's another issue. But you see difference in the axis of the loading, basically, from thermal stresses.
At least on the Shiba, well.
Okay, Roy.
One
I
question.
never, okay. I never answered Kai's first question.
Well, but never mind.
You know, there is an expression we use sometimes that if it looks like a duck, and it walks like a duck, and it talks like a duck, maybe it is a duck.
Oh, but that is a practice. Industry says that always, but I hope that scientists wouldn't revert to that.
Oh no, I don't use that argument in anything I've written.
Okay, Roy.
So to challenge again your argument, I was wondering, you mostly discussed sea ice on the geophysical scale. So my question is basically about the aspect ratio, like length and thickness. Is your argument is still consistent where, for example, you study fractures in glacier ice, which is roughly the same horizontal extent as the dimensions you mentioned, but the thickness is much larger?
In principle, I think it would. Of course, the aspect ratio in the ice cover is very, very large, you know, thousands of kilometers to a few meters. Huge aspect ratio.
Well, for example, Larsen Sea, which is very large reef.
Yeah. I see no reason why this way of thinking would not apply. But of course, in glaciers, we're not so much in the regime of brittle behavior as we are in the case of a sea ice sheet. A lot of creep going on. Certainly in the vicinity of crack tips, there will be creep and crack propagation. There'll be an interaction of the two processes competing one against the other to dominate and govern the behavior. But I don't see why the ideas wouldn't apply there, at some level at least.
Bob?
Just a comment on the comb cracks, an interesting thing that we observed many years ago. Martin Rist was in St. John's and we were doing experiments on bicrystals and single crystals. So we made a bicrystal, pretty big sample with a 45-degree angle between, at the interface angle was 45 degrees. And then we put a small amount of compression on that and then apply uniaxial stress. And we saw the same comb features, but the interesting thing was that we didn't have to make thin sections. They ran through the whole thickness of the sample.
I can believe that because of the single crystal nature of the material.
Yeah.
Yeah, I believe it. Yep, I sure would.
Well, I think we can thank Erland.
Danny had one.
Well, I mean,
Okay, one more.
Well, okay. Well, I should really let Erland answer Kai's questions, although I would love to. Okay, but just to make one comment, ice arching exists. Okay, so in the Fram Strait and Nares Strait, etc., you see ice arches. Ice arches cannot exist if there's no tensile strength. Ergo, there is tensile strength.
Thank you.
Let's thank Erland for a very helpful